models and temporal response functions. So before we start our presentation, we just want to say we are really excited about this workshop, and we would like to thank the organizers for inviting us here and giving us the opportunity to share our experience with you. We already had a wonderful introduction in session 1 by Jonas Oblieser and Ed Lehler, and they already explained a lot. But I would like to start our presentation with first explaining why and when we are using encoding models. So let's start here with a picture of my brother, who was a participant in one of my EEG experiments during my PhD. And so, he was listening to a natural continuous speech stimulus, on which we will focus today in this presentation about encoding models. And so, all my participants were listening to audiobooks or sentences because we were interested in how the brain responded to these ongoing stimuli. And so we were measuring their time-locked brain responses, as Jonas Oblieser already told you about, using EEG. And the important part about encoding models is that we can really focus on how these brain responses look like, and therefore we use the temporal response function. So I did many of my experiments in the lab, and I just also want to highlight here that with encoding and decoding models, we can really make this bridge from the lab to daily life scenarios pretty easy. So we can use these models in combination with mobile EEG systems. And also, a lot of models are used by many researchers to develop neurosteered hearing devices, such as self-fitting hearing aids and cochlear implants, and then use the EEG responses to fit these devices. So so in the remaining of the talk, we will of course focus on the encoding model, but also a bit on the experimental design of these encoding experiments. So you already know that we have an ongoing stimulus, which is sometimes 10 minutes long, because we like to use audiobooks. And so before we start on the several steps we do in an encoding model to analyze the stimulus and the EEG responses that we recorded, I just want to highlight a few guidelines, which are no strict rules, but a few guidelines that we would like to give you about designing these experiments. So first of all, there's no strict rules. So it really depends on your research question, what stimulus you take, and also what conditions you need and so on. But for example, in my PhD, I chose to use sentences instead of audiobooks because I was really interested in the link between speech understanding objectively measured by recalling scores and their EEG responses of my participants. But you can also use audiobooks because you're more interested in daily life applications, for example. So with regard to the stimulus, it's, in our opinion, very important to not make the stimuli too short, because otherwise you will not get a good model fit. And with regarding to encoding models, you will not get a proper temporal response function. So we usually have at least 10 minutes of stimulus or data to fit our temporal response functions. And this means that you can have multiple trials of, for example, 1 minute stimulus, or you can really have a single trial stimulus of 10 minutes of an audiobook. Important is also here that you don't make the stimulus too long, so that you include breaks, because attention can really affect your temporal response functions. So don't let participants listen for 4 hours, please. Then regard to the methods that we use, so we use MEG and EEG because these are highly, they have a high temporal resolution, which is very important because we're investigating time-locked brain responses. And one remark that I want to make is that triggers are a very important part of your experimental setup, because you need an alignment between your stimulus and your brain responses that you're recording. And these triggers should having a millisecond precision, because otherwise you cannot interpret the latencies of your temporal response functions. And then lastly, yeah, pilot your experiments and recruit enough participants. So yeah, now the encoding model. So as Ed Layler and Jonas Oblizer already talked about a lot, is that an encoding model goes from the stimulus towards the brain responses. And so you use a temporal response function to map your stimulus to your predicted brain responses. So you go from the stimulus to the brain responses. And so in this talk, we will mainly focus on a single stimulus feature. And so the temporal response functions that are plotted in this presentation also are specific to that speech envelope. Yeah, so one last remark I want to make is that the temporal response function also is not the length of your stimulus or your predicted brain responses, but is usually has a time window from 0 to 500 milliseconds. Okay. And yeah, and then the last item, what later also talked about, is the encoding or the prediction accuracy. So many researchers correlate the predicted brain responses, the output of your encoding model, with the actual brain responses to get an idea of how well the stimulus feature is encoded by your brain. Okay. So before we go into the algorithms, what Joshua will talk about is I'm just going to briefly go over the temporal response function one more time, which is one of our outcome measures when we're talking about encoding experiments. So here you can see the temporal response function for the speech envelope. And so it's often compared with auditory evoked potentials, because these have similar shapes as the P1N1 P2 complex. And so we use this temporal response function, which is very interesting if you're interested in how the brain responds to our stimulus in terms of amplitude and latency. And so one big advantage of using the TRFs against, for example, auditory evoked potential is that with this single natural continuous speech stimulus that we present to our participants, we can actually extract multiple features. So we can extract the speech envelope, but we can also extract phonemes and then calculate TRFs for that. Okay, and then our second outcome measure for encoding models is that we calculate the prediction accuracy, which is the correlation between the actual and predicted response. And so these prediction accuracies have a typical small value, as you can see here on this graph. And so these typically range from 0.01 to 0.1 or 0.15. And yeah, this is because in the brain, not only your brain responds to a single stimulus feature, such as the speech envelope, but a lot of other processes are going on. Okay, then now I just want to give the floor to Joshua, which he will talk more about the algorithm use when using techniques.
Thank you, Lien, and thanks again to the organizers for this great workshop. So I'm going to be talking about the methods that go into building these TRF models. So we can view our TRF as a convolution model, where if you have an impulse-like stimuli, there is an evoked response in the brain, and these evoked response will get convolved with the stimulus, and that will show up in your EEG or MEG response. If you have some stimuli that are close together, these evoked responses may overlap. And if you have scaled impulses, then you will also have scaled responses. So this is a very simple conceptual way of looking at the TRF. When you think of continuous stimuli, you can think of the fact that every time point in that continuous stimuli has an evoked response that overlaps and is scaled, and that will show up in your EEG or MEG signal. And so our goal is to find this function that maps the stimulus to the response. And so here you have the stimulus convolved with your TRF, and that will give you your response. So the convolution, once again, is just a weighted sum of lagged values of the stimulus. So to actually find this temporal response function, it's easier to formulate it as a regression problem. And so here, once again, you have the convolution And I'm also adding noise here, which may mean other neural processors as well as experimental noise. And to formulate this as a regression, we can form this matrix of lagged stimuli, and K is a number of lags in your TRF, maybe around 500 milliseconds. And when you multiply this matrix by your TRF vector, you would get your response vector, EG response or MEG response vector. And this is a simple regression formulation for dependent, independent, and weights of your regression. So to solve this, once again, we have our actual response, and then you have our predicted response based on an estimated weights. And we want to find the TRF, or the weights, that minimize the mean squared error between your actual and the predicted response. And we have the familiar least square solution for regression for that. So this is one way of solving this problem to find your TRF, but there are some problems with this least square solution. It can be unstable because you're inverting this stimulus matrix, and so that could lead to overfitting, to noise, and also for your solution to be very sensitive to rounding errors and things like that. It can also lead to biologically unrealistic TRFs with a lot of high frequency fluctuations and so on. So to solve that, we can use regularization. And in this, we are going to talk about ridge regression, where we just make a small modification to the regression solution by adding this lambda I. And this lambda parameter is a regularization parameter. And so this will pull down our regression weights and make them smoother, and also reduce the dependence on this matrix. And so here you see what this regularization actually does to the TRF. Here you have a TRF without any regularization, lambda equals 0, and you see a lot of fluctuations even before 0 in time lag, which may not be meaningful. And then when we optimize our lambda, we find that the TRF is much smoother and maybe easier to interpret. You can also increase your lambda even further, and then you would find that the TRF is too smooth and maybe you're losing some of the details that you would like to keep. So another consequence of increasing lambda is that the model weights would reduce. And so what's important is the shape of the TRF, or the relative amplitudes of the peaks and latencies, rather than the actual absolute weights that are used. So once again, the ridge regression is implemented in the MTRF toolbox, and there'll be much more about the MTRF toolbox during all the hands-on tutorials. So how do we choose this regularization parameter? We can use cross-validation. So here we would separate our data into training and testing sets, and we would fit our TRF models for each lambda we are interested in on training data. And we'd evaluate the model performance on testing data and choose our optimal lambda. So here is a range of lambda values, and then we fit TRF on training data, and we predict our signal, find the correlation with the actual signal, and wherever the correlation is highest, we would say that that is our optimal lambda. So once we can estimate a TRF at one sensor, we can estimate independent TRFs at each sensor or channel. And that would give you something similar to an evoked response, where you can see a topography of the TRFs. And this was all talked about in previous talks as well. We can also go one step further. If you can source localize your EEG or MEG data, you can find source localized TRFs. And that will give you an understanding of where these peaks occur in the brain. We can also consider multivariate TRFs, or MTRFs, where we are interested in different types of predictors and features. And again, this was mentioned in some of the previous talks, where we have not only acoustic features, but also some phonemes, phonetic features, as well as some linguistic features. And if we simultaneously estimate TRFs to all these features, they can compete against each other to explain the variance in the signal. And you will get TRFs that may look different for each feature. So here is some prior work by Christian Brodbeck showing that there are different TRFs with different latencies for these linguistic features. So there'll be much more about these multivariate TRFs in Aaron's talk later today. Finally, I just want to mention an alternative to ridge regression, which is the boosting algorithm. And this also is a way to estimate TRFs. And this is an incremental approach where we start with an all zero TRF, and then we add or subtract a fixed small value at each lag of our TRF. And so here you see that there is a small value that's added or subtracted, and then we have our predicted signal based on those small values. And we find the error of that predicted signal with our training data, and we keep the change that gives us the least error and add that to our current TRF. And then we have our predicted signal from our current TRF correlated with a validation data set that was not used for training. And if this improves the correlation, then we will do this loop again. And so here you can see that we are incrementally building up our TRF as long as the correlation with unseen data improves. So boosting will give you TRFs that look in broad respects similar to ridge regression, but it will look different in the sense that boosting gives you sparser TRFs. You can see these two TRFs were for the same data, but ridge regression is much smoother and boosting is sparse and has narrow peaks. However, one advantage for boosting is that you don't need a regularization parameter, and so you don't need to tune that. And this can be useful because tuning that lambda for multiple predictors is quite complicated. And we can also use cross-validation to reduce overfitting. So the boosting algorithm is implemented in the EELbrain software for Python, and Christian Brodbeck will talk more about that tomorrow. And with that, I'd like to hand over back to Lien to talk about the interpretation of TRF models.
Thank you, Joshua. You can see my screen, right? Yeah.
Yeah.
Okay. So now in the last part of this presentation, we will talk about these two outcome measures, the temporal response function and the encoding or prediction accuracy, and how we should interpret these measures. Most researchers start actually with the prediction accuracy when explaining their results in the papers. And so this is because you can actually not see these two outcome measures separately from each other. So if you, for example, have a very low and not significant prediction accuracy, then probably it's also not a good idea to interpret the temporal response function for your participants. So first step that we do is we do not immediately apply statistics on these accuracies, but we first visualize them and prepare them a bit. So as you can see here in this graph from a recent paper, the encoding accuracies are plotted as bar graphs for the different conditions and also for a hearing impaired and a normal hearing group. And you see again that these values are pretty small. The first thing to do is to check whether your prediction accuracies are above a certain level, which is the noise floor or a significant level, here indicated as a yellow bar on the graph. And so you can calculate this noise floor or significance level by, for example, instead of the stimulus feature, for example, the speech envelope in which you're interested in, instead of using that feature to feed your encoding model, use a shifted version of that speech envelope or use a completely different speech envelope from another audiobook to use that as an input for your encoding model, calculate the TRF as Joshua just explained, and then also calculate the prediction accuracy for that noise floor stimulus. And then this will give you encoding accuracies that are close to zero because that stimulus was not presented to your participants. So another way to plot your prediction accuracies, because you have a prediction accuracy per channel of your EEG or MEG system, is using topographies. And what most researchers do is use a dimensionality reduction method to go from all these encoding accuracies for a single subject to just go to one value. So for example, in this paper, they just selected the frontal central electrodes for every subject and then averaged the encoding accuracies for that selection. And then they had one value per participant. Okay, and then the next step is, of course, use statistics to draw conclusions for your results. So to compare conditions or groups, you can see, for example, in this figure here, we were comparing normal hearing and hearing impaired subjects. And the encoding accuracies are also plotted here on the y-axis as a function of speech understanding. So just two things I want to highlight here is that it can sometimes happen that you have negative correlations, which is most interpreted as noise, and the higher correlations mean that the stimulus is more encoded in the brain, but that does not necessarily mean that that's better for your participants. Ed Lailier also briefly mentioned that hearing impaired participants or older participants have these exaggerated encoding accuracies, and so we do not know yet what the exact reason for that is. Okay, and then our second outcome measure, which is the temporal response function, which is a big advantage when you're using encoding models, because you can get more insight in how the brain responds to your stimulus feature. And so, as Joshua already showed, you can use different visualizations to plot these, but we often also use a dimensionality reduction method to go from every TRF for every channel of your system to just go to one TRF per participant. For example, we use here PCA to do that. And then the next step is to use a peak picking method per subject to analyze the separate peaks. So this is now a TRF for the speech envelope feature. But so we use time windows for the P1 and 1 P2 peak. And these time windows can change depending on the subject group that you're interested in. So normally for normal hearing subject, that's 50, 100, and 200 milliseconds. But for example, if you have hearing impaired participants, these time windows could be a bit later. Okay, and then it's very important to also check your peak picking methods for each individual subject. For example, for this figure here, for subject 1, we see that we have 2 peaks, but P1 is not clearly, we cannot clearly see P1 here for that subject. So then for our statistics, we usually set this peak then to an amplitude of 0 and latency to not a number. What also can happen is that you just have very noisy TRS for a particular subjects, and then you cannot really do something with their temporal response function. So that's also good to check their encoding, the encoding accuracy for this subject, or apply additional pre-processing step to clean up the data. Okay, and then of course, we will also use statistics to draw our conclusions. So cluster-based statistics can be used when you don't want to use a dimensionality reduction method, or you can just perform an ANOVA or linear mixed effect model on the amplitude and latency values of the temporal response function. Okay, so now we are at the end of our presentation. So we were talking here today about linear encoding models and how we can use this to predict time-locked brain responses from a speech feature, in this talk particularly the speech envelope. So the big advantage of encoding models is that you can use or interpret the temporal response function as an outcome measure, and so get more insights into the brain response. With regard to designing your encoding experiments, there are no strict rules, but yeah, keep in mind your research question and make decision based on that. And also do not make the stimulus too long and also not too short, and use triggers that perfectly align your stimulus and brain responses. The algorithms used for encoding models were nicely explained by Joshua. And so you can use ridge regression or boosting, and these two methods will also be more talked about in the hands-on tutorial or tomorrow during the mini session. And then lastly, the two outcome measures that we're all interested in, I think, with regard to our research, so the prediction accuracy and the TRF, or the temporal response function. Okay, thank you very much for listening. And if you have any questions, we're happy to answer them.
Thanks, Lien and Joshua. That was really great. So we have one question in the Q&A right now. Is there a way in the toolbox to compute the noise ceiling as well? It would be informative to see how much a given feature set accounts for the explainable variance. I know you've told me you work more with EEL-Brain than the MTRF toolbox. So I'm curious, I guess, if you can speak on EEL-Brain, whether or not you can get noise ceiling with that toolbox.
Yeah, I mean, you can compute a noise level by using either something like shuffle predictors or shuffle features, something like that. And that would give you an estimate of the noise. But you would have to do that in your brain yourself, I think. I'm not sure how the MTRF toolbox, maybe Nate, you can talk about that, how it's implemented. I think in your tutorial, they're going to go over it, right?
Yeah, I'll talk a little bit about that in my tutorial on getting a null distribution. Gal Chen asks, was the accuracy of encoding decoding compared between boosting and ridge regression fit?
We didn't compare the encoding and decoding accuracy between boosting and ridge regression, but from my latest analysis, I know that, for example, in U-brain, so using boosting, we sometimes have lower correlations with regard to the encoding model, because we actually do not only use a training and a testing data set, but we also actually calculate the prediction accuracies on a third unseen data segment of your data. So you actually, and that makes actually the correlations a bit lower, but a bit more trustworthy. So maybe Christian Broderick will give a presentation on that tomorrow. So maybe that will come there too.
Okay. We still have some time for a few more questions. Oh, Talat Jabin asks, how much does the shape of TRF change depending on the features of the stimuli?
So the features of the stimuli will be, I think, covered in one of the next talks by Aaron. So yeah, your feature, as Ed later also really mentioned in the introductory session, your feature really defines how your TRF looks like. So I mostly use the speech envelope. I didn't use many linguistic features or other features, but I know that, for example, if you use more linguistic feature, that you get this N400 response. So it's not a typical P1 and 1 P2 peak then. So yeah, it really changes. So it depends on your feature. Joshua, do you want to say something extra?
Yeah, I agree. I mean, it really depends on what the feature is, and a higher level feature may lead to later responses or later peaks in the TRF and things like that.
Okay. I actually have a question. I was wondering if you've worked with any behavioral measures and looked at how neural tracking might correlate with behavioral measures. Like what sorts of speech features seem to correlate better if you've looked at that. I was just curious on your thoughts.
Yeah, so during my PhD thesis, I worked with speech intelligibility and how I could use the neural tracking of the speech envelope using decoding models then to predict speech understanding. And so for me, that's nicely, well, I didn't use a correlation, but I got really, a significant slope for my linear mixed effect models. So when persons were really understanding the speech better, because the signal to noise ratio was better, then their neural envelope tracking or their decoding accuracy was also much higher. So that was one of the behavioral measures that I used. I also used cognitive scores on inhibition tests, such as the Stroop test, and that seems to also correlate with these decoding accuracies. So yeah, a lot of researchers try to use these decoding and encoding accuracies and using the peak amplitude and latency of the temporal response function to explain behavioral measures. Joshua, do you want to also say something?
No, not really. I haven't worked with behavioral measures directly. But I think one of the main issues is finding a good behavioral measure for continuous data, as was already mentioned. But yeah.
Yeah, so
Makes sense.
that's maybe something I want to comment on, is that's the reason I use sentences during my EEG experiments. And I really asked the participants to recall the sentences actively during the EEG experiment. So I had in real time their behavioral score for the sentences as well as their EEG measure, which is much more difficult if you have audiobooks. And for that, I would advise to use ratings instead of questions, because you have to ask many questions to get a trustworthy outcome measure for that.
Okay. We have another question here. Magdalena asks, would you expect different answer of the noise floor calculations using shuffling the stimulus features and a fixed TRF over deriving new TRFs using shuffled feature and comparison, and the prediction of shuffled versus unshuffled stimulus features? So I can partly answer this question. I know Aaron and I will be discussing this a little bit in the hands-on tutorial later using the TRFs. So we've worked with computing null distributions of prediction accuracies, but also shuffling stimulus features to get noise floor. Do you have any other thoughts on it, Lien or Joshua? Okay. So if there are no other questions, thanks Lien and Joshua again for the talk. And our next talk is Laura Gwilliams. Laura Gwilliams received her PhD in psychology with a focus in cognitive neuroscience from New York University, and she is currently a postdoctoral researcher at UCSF. She uses MEG and ECOG data to understand how linguistic structures are parsed and composed while listening to continuous speech, and she'll be talking about decoding models.
Thank you very much. I also want to start by just thanking the organizers for putting together this really great workshop. That these things are a lot of work to organize, and I think they've done a really good job. And I'm excited to both be a part of it as a presenter and as an attendee. Okay, let me share my screen. Share this. So unless something looks completely wrong,
That's good.
Yeah, tell me. Okay, great. So I'm going to talk about decoding analysis. My plan is to spend the first 20-ish minutes giving kind of a formal presentation, and then I've kind of coded up the things that I talk about in the presentation. So I wanted to kind of give a live demonstration of how you would actually implement these kinds of analyses to analyze MEG data, but this could be applied to different kinds of data. Okay, so what I hope is that by the end of my talk, this is what we will have covered. So first, I'll briefly talk about kind of what is decoding, and mainly what I want to do there is kind of to demystify. I don't know about you, but before I knew about this stuff, it was like the decoding is this kind of like analysis magic that you apply, and it's, I don't know, somehow fancier than other things, or I don't know, it has some kind of mystification around it. So I first want to just like blow that away. I'll talk just very briefly about why we might want to choose a decoding analysis to analyze data. And then really the bulk of what I'm going to talk about is basically the practicalities of how you actually implement a decoding analysis. What kind of decisions do you need to make? What motivates those decisions? And then, as I said, we'll hopefully have some time to actually look at code which implements all of these things. So by the sounds of it, sorry, it's early where I am, so I didn't get to see the talks this morning, but from what I just saw, it seems that this kind of idea is already put forward. So with an encoding analysis, what you're trying to do is to predict or to analyze brain responses as a combination of stimulus properties. So maybe what you're trying to do is to model a neural response in a single EEG sensor, for example, as a combination of a bunch of properties of the stimulus that kind of led to the response that that EEG sensor would pick up. With a decoding analysis, basically we're just going in the other direction. So this would mean that we're going to be modeling, we're trying to predict stimulus property from a weighted combination of neural responses to that stimulus property. So this would mean that, let's say if it's an EEG study, that we're going to take the responses across, say, all of the sensors or multiple sensors and use that to try to reconstruct what the stimulus feature was, which led to the response across all of those EEG sensors. So there's nothing really fundamentally different between taking a decoding approach or an encoding approach. It's the same numbers basically that we're trying to learn kind of a mapping between. The only difference is, are we trying to predict brain responses as a linear combination of stimulus properties, that would be encoding, or are we trying to model stimulus properties as a weighted combination of neural responses, and that's decoding. And yeah, so that's kind of where I wanted to start off by saying this isn't fundamentally different. We're basically just switching around what is X and what is Y in our equation. So this is just the formula for a linear regression. And I just want to briefly just kind of remind everyone what kind of goes into this. So we have Y, this is the thing that's being predicted. We have our intercept, and then we're going to have a bunch of different features that we think are relevant for reconstructing or for predicting this property Y. So we'll have a given feature, and then we need to learn a weight or a beta coefficient which gets applied to that feature. Maybe this is for feature 1, and then we'll have again for feature 2, for feature 3, blah, 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 and we can have as many features we want. And then at the end, we have basically the variance that we can't explain given all of these features in the model. So just to kind of re-say what I just said, but in different terms, when we're taking a decoding analysis, what we're trying to do is to reconstruct the stimulus property. So that means that Y is going to be a property of the stimulus, and then each of these little X's, X1, X2, X3, this is going to be a different brain measurement, basically. So maybe this could be, here it could be an EEG sensor, or it could be a voxel in the brain, or yeah, any given brain measurement that you think is relevant for reconstructing the stimulus property you're interested in. So this means that for each stimulus property, we're using multiple brain measurements to reconstruct that property. And with an encoding analysis, as I said, we're going in the other direction. So this is trying to predict, so Y becomes now a brain measurement, and instead our X's are multiple stimulus properties. So this means that for each single brain measurement, we're using multiple stimulus properties to reconstruct that. So what this again means is that for decoding, we have what we're trying to predict is the stimulus feature given the brain. And sometimes decoding is kind of talked about synonymously with multivariate analysis. So it's multivariate in brain space, but it's often univariate in kind of stimulus language space. Whereas for an encoding model, this is, I mean, technically it's also multivariate, but it's multivariate in the stimulus space and univariate in the brain space. Okay, so that I think is, yeah, something that I thought was important to get across, just that what the distinction here is what is it that you're predicting, and are you using multiple brain measurements to reconstruct the stimulus, or are you using multiple stimulus features to reconstruct a single brain response? Okay, and just briefly, some reasons why you might want to employ a decoding analysis is, well, one, if you are dealing with low signal to noise brain measurements, then there can be a advantage to grouping multiple brain signals together to perform the analysis rather than using kind of a single response. And this is linked to the fact that if what you're trying to do is reconstruct a neural response, there's only so much variance in that neural response, which is actually linked to the stimulus property. So this means that it will be hard to actually be able to account for a lot of variance in the neural responses. Whereas if you go in the other direction, you might be able to fully reconstruct a stimulus property using multiple neural responses, because essentially there's less noise in the stimulus property that you're trying to reconstruct as compared to the neural responses that you're using to reconstruct that. Another aspect here is that when we're performing this decoding analysis, we're essentially trying to learn, let's say, a spatial pattern over, let's say, MEG sensors. And one nice application of a decoding analysis is to see whether this pattern that we learn for a given stimulus contrast can be equally used to discriminate a different set of contrasts. And then you can start to make claims that there is some kind of shared neural correlate between these two scenarios. So that's another case in which decoding can be useful. Okay, so the main bulk of what I want to go through today is basically what are the different steps, like what's the pipeline of actually implementing a decoding analysis, and what decisions do you need to make along the way. So I've broadly identified these 4 steps, and I'm basically just going to go through each of the 4 steps in turn. So, okay, step 0 is, okay, we need to split our data into data that we're going to use to fit our decoding model, and which needs to be separate from data that we're going to use to evaluate the actual accuracy or performance of that decoding model. So as I said, our goal here is to see how well we can reconstruct the stimulus feature given the neural responses to those features. But in order to do that fairly, we need to train the data on essentially an independent set of data from that which we're evaluating. Otherwise, if they're not independent, if we train on a set of data and then evaluate the accuracy on that same data set, we're going to overestimate how well our decoding model actually performed. So in its simplest form, this basically means that we take all of the data in our experiment. So let's say, I don't know, we had 1,000 trials, and we're going to split those 1,000 trials. Maybe I take 800 trials and I use that to train a decoding model. And then on the remaining 200 trials, I can use that to evaluate the accuracy of that model. And in order, rather than just doing this once, typically you will split the data into different partitions, so train and test, and then loop through all of the possible non-overlapping combinations of those partitions so that you get essentially five different estimates of how good your decoder is. So one for each different partition of the data into train and test, and then you can see, usually on average, averaged over these different ways of splitting the data, how good did your decoder perform. So as I said, this is a decision that you need to make as the analyzer, and there are different cross-validation schemes that one can choose. There's actually many of them, but I'm just going to highlight 4 just to kind of give you a sense of what the, I guess, space of decisions might be, and again, why you might want to choose one or another. So one is k-fold. This is basically what was shown on the previous screen. And in this case, so what this plot is showing is, so if these are all of my 1,000 trials, in the first split of the data, I'm just going to take the first quarter, and I'll keep that aside as my testing set, and then I'll be training on everything else. And then I'll get some kind of accuracy measure. And then in my second iteration, I'm going to use the second quarter to test the accuracy. And the third iteration, I'll take the third quarter, et cetera, et cetera. So that's one way in doing it. And the k-fold, k just basically is how many folds am I using to, how many times I'm going to iterate through this data, how many times I'm going to partition and evaluate the accuracy. You might have come across the, so I think that k-fold maybe is something you've come across. Stratified k-fold means that, again, you're partitioning the data, but the stratified part means that you want to make it so that the trial types that you're testing and training on are representative, so of the full data. So in this case, the experiment, I guess, was designed that say there are three different conditions, let's say, and the first type of condition was presented, I know, the first 10 trials, and then we have the next 30 trials, and then so here what we're training and testing on is not actually representative of all of the different trial types, whereas here we're going to pick out trials so that the portion of trial types of 1, 2, 3 are the same in what we're training and testing, and also, yeah, representative of kind of all of the trial types in the experiment as a whole. So I guess maybe a simpler way is to say, okay, if you are trying to decode just a binary variable, and there are, in 80% of your trials is class A and 20% are class B, you want to make it so that when you're training, you're actually training on a 80-20 split of the different trial types, rather than in one split having 50-50 and a different trial type having 20-80, so that everything remains consistent. Okay, so another approach would be, rather than taking consecutive trials in this way through the experiment, which you could already see being potentially problematic, because, I don't know, even let's say the participant got, I don't know, sleepy towards the end of the study. This means that the trials that you're training on might actually be fundamentally different from the trials that you're testing on, and this is going to have potentially negative consequences on the decoding accuracy. So another possibility is just to randomly select trials throughout, like kind of evenly or randomly distributed through the course of the experiment, rather than picking consecutive chunks of trials. And again, you can do the same thing, but rather than being completely random, the selection of trials can be pseudo-random, so that you always retain the proportion of trial types in what you're training and testing, as compared to the full data set. Okay, So yeah, so those are some different types of cross-validation schemes. And I would say that typically it's typical to train on about 80% of the data and then evaluate on about 20% of the data in any given split. Okay, so having picked what kind of cross-validation scheme we want to use, now we can actually start training our model. But there's another decision that we need to make, which is, okay, what actual decoding algorithm are we going to use here? So decoding of itself, it doesn't really tell you anything. You need to decide, okay, what model am I actually going to try to optimize? And in fitting this model, so this is the equation. If we chose a linear model, this is the equation essentially that we'd be trying to optimize. And in this step, our goal, the output of this stage, is going to get these beta coefficients. And if you remember, the beta coefficients are these, each of the weights which we use to weight each of the features into the model. Okay, so that's our goal, to get out these coefficients. But first, we need to pick what algorithm we're going to want to use. So the, I guess, kind of like gross decision here is, okay, what kind of analysis are we actually applying here? So is it a classification analysis? And that would be when Y is categorical. So the stimulus property that we're trying to predict is binary. So this would just be kind of an overlook of what that would look like. So X, those are our brain measurements, and each kind of row of this thing is a schematic of a different trial. So for each trial, we have a brain measurement across all of these different sensors, and each trial is associated with one stimulus property. And in this case, that stimulus property is either 0 or 1, so it's a classification problem. Just be like, I don't know, is the word that the person is hearing a verb, for example? No, it's not a verb. Yes, it's a verb. No, it's not a verb. Yes, it's a verb, etc. Okay. On another possibility is that actually the analysis that we're applying, so the stimulus feature that we're analyzing, isn't binary, and instead it's continuous. So that would be a scenario, something more like this. So again, for each trial, we have our bunch of brain measurements, but now we're associating a stimulus property which has a continuous variable. So it's not just 0 and 1, it can assume any value. So maybe this could be some kind of normalized measure of word frequency or something like that. Okay, so if we're dealing with a classification problem, then one possibility is to use something like a logistic regression. It's not the only possibility, but it's probably one of the most simple and also very commonly used. And if we're using a logistic regression, then this is the formula that we're going to use. This is what we're going to try to optimize. Whereas for a continuous feature problem, then we're going to want to use a linear model. So in this case, this would just be a linear regression model. And again, this isn't the only possible option when having a regression problem. And yeah, actually I got this from scikit-learn. If we're taking a broad, so these are different algorithmic options that you could pick given a classification problem, and these are some different options you could pick given a regression problem. So there are the different algorithms that you might want to choose, and there are different reasons why you might want to choose one algorithm over another, and some of those kind of decisions are outlined on this figure here. So some relate to how much data do you have, and how many features are you actually trying to use to predict a given property. Okay, but for now, we can make kind of a broad distinction between classification, in which case we might want to use a logistic regression, or a regression problem, or you might want to use a linear regression. Okay, so I've skipped over regularization because I think I don't have time to give that topic justice, but that I've also put that here because that's also something that kind of has to be optimized. But that also is related to the algorithm that you select. So, okay, having selected the specific algorithm that we want, we can train that algorithm and get out our coefficients. And so the next step then is to take the coefficients that we learned given the training data and then apply them to the brain data of the held out brain data in order to get a prediction of the stimulus property for the held out test set. Okay, and I wanted to kind of give this little schematic of what it means to go from fitting a model to actually generating a prediction from that model. So when we're fitting our analysis, or when we're fitting our algorithm on the training data, we're basically we're learning a line basically. So we're trying to get in a classification problem, what is the decision boundary which distinguishes class A from class B. And here I've kind of simplified the space so that it's just two-dimensional, that we have this class of features. So each dot would be a different trial basically. Each trial is defined relative to its response in along sensor 1 and sensor 2, although it's going to be many more sensors than that, but I can't visualize all of that here. So it's defined relative to its neural response, as well as what class it belongs to. And given all of that information together, we can fit the line which seems to best distinguish class A from class B. So when we go over to the testing stage, this is exactly the same line. So this is the same line that we learnt from the training data being moved over here, but now each of these dots is the held out, the response to the held out data. So on, I don't know, held out trial 1, the neural response to sensor 1 was 1, sensor 2 was 2. And over here, this dot means that the neural response on that trial was around 6.2 and 4. And so we basically take all of the responses to the held out data, and the algorithm looks at them relative to the decision boundary that it learned in the training stage. And then we can assign labels to each of those trials, essentially based on what side of the line did that trial fall. And yeah, that's essentially how we get predictions of the classifier in the test set. And again, I should say this is visualizing just a two-dimensional space, so which is this one. But in reality, the dimensionality of the space that we're dealing with is as large as neural measurements that we're using to try to distinguish the stimulus property. So if we have 306 MEG sensors, then what we're dealing with is a 306 dimensional space, which means that, well, the decision function that we're learning isn't actually a line, it's a hyperplane in this high dimensional space. But so that our brains don't explode, we can conceptualize it as, yeah, let's say like a two-dimensional plane in a three-dimensional space. And I like this quotation from Jeff Hinton. The way to understand high dimensionality is to visualize it in 3 dimensions and just say, 14 very loudly. Okay, so that is then how we get the predictions of our held out data. And then the final step then is to take so these are the predictions of those held out trials. And this is the truth of what the label actually was on those held out trials. And we want to try to see, well, how good did we do? How close are the predictions to the truth of those properties? And the next decision we need to make is how we're actually going to perform, or how we're going to score it in order to get a performance measure. Okay, so this is again partly what's going to decide what scoring metric you use. Again, will depend on if you're dealing with a classification problem or a regression problem. So if we're dealing with classification, then the way we see whether our predictions are close to the truth is basically going to be different than if we have continuous measures in both cases. And again, there are a lot of different metrics that one can use to evaluate performance. Here I just took screenshots of the different metrics which are implemented in the Python package scikit-learn. So for a classification problem, I guess the simplest thing, or simple, I don't know, they're all kind of simple, but maybe the one choice is accuracy. So you basically just see, okay, if the truth was 0, if the prediction was also 0, then yes, you got that right. So this is, yes, a correct trial. And then here the truth was 1, but the prediction was 0, so that's an incorrect trial. You just basically sum up all of the times that it was correct, divided by how many trials there are total, and that's going to be your accuracy score. Yes, although I would say that, again, just from my experience, I typically use the ROC, AUC as a scoring metric, which is nice because chance is always at 0.5, regardless of maybe an imbalance in the number of actual positive instances of the class that you have. So that means that you can group together classes with different imbalances in the number of trials, and chance is always at 0.5, which makes them directly comparable. Whereas something like accuracy, the chance performance is always going to be basically the ratio between positive and negative classes, which can be a bit of a pain if you're trying to combine features together. And with a regression type analysis, again, there are different metrics that you can use, and it's always possible to implement your own. So I often will use a Spearman correlation, for example. A rank correlation to evaluate the accuracy of a regression decoding analysis. Okay, good. So those are essentially the basic steps that go into a decoding analysis. And you can essentially see it as a pipeline. So if this is my function, these are the inputs that you need to provide to that function. So these basically corresponds to the decisions that you need to make, and then these will be the different steps that need to be performed to eventually provide a performance score at the end of the day. So okay, I think I have a little bit of time, so I want to just briefly show you basically this pipeline, but in actual code. Okay, so hopefully you can see this. So yeah, again, you should be seeing a Google Colab notebook right now. So here I just wrote out a notebook with some data that comes from a publication of mine and John Remy King, and I wanted to make this notebook and the data available so you can kind of play around with it and yeah, edit it for your own purposes too. Yeah, I guess just briefly, the way that I usually do these analyses is by heavily relying on scikit-learn toolbox for Python, which is honestly an incredible resource, not just for the code itself, but it has a lot of tutorials and it has a lot of kind of nice visualizations of, yeah, kind of the different aspects which go into analyses. So yeah, so thank you to those developers for creating that. Basically here we're loading MEG data. There are a bunch of different subjects in this folder, but I'm just, yeah, just working with one subject at a time. So if I, okay, let's see if this is actually still loaded. This is like, okay. Yeah, great. So these are my epics of the MEG data. This is how many trials I have. This is how many MEG sensors I have for each trial. And this is how many time points in the epic. Each trial is basically, has a bunch of stimulus properties associated with it. So each trial is a row in this data frame, basically. So this was in this study, the participants were looking at symbols which were varyingly ambiguous between letters and digits, and different properties of the stimulus is inputted into this data frame. So there are different, let's see, there are different features that we might be interested in, but what I want to do for time is just to kind of show what the code would look like for each of those different steps that I just described. So here I'm just going to be applying the analysis to one time point. Usually what I do here is loop through time. Yeah, so here I'm just applying the analysis to one time point. We get the matrix of the epic data. So this is going to have a shape of number of trials by number of sensors or channels. Then we also have y, which is just a vector corresponding to the stimulus properties. So in this case, it was the symbol flashed on the left or the right side of the screen. Okay, so that's setting up our X brain matrix and our Y stimulus vector. And then there are various decisions, as I said, that we need to make. So the first is, what cross-validation scheme do we want to use? Here I chose shuffle split. So this would be the one on the bottom left of the slide that I showed you. So we're going to randomly pick out trials along the length of the experiment. So we just get the indices of what we're going to train on and what we're going to test on. This is a classification problem. So if I show you Y, you can see, oops, if I reload Y, then you can see that Y is just a bunch of zeros and ones. And so I'm going to choose to use a logistic regression algorithm to make that classification. And the scoring metric that I want to use is going to be the area under the curve. Okay, So then we're simply going to fit the logistic regression on the training data. So we give it the training trials of the brain and the training trials, the corresponding labels. And here I'm visualizing the coefficient. So this is the coefficient that was learned for each channel of each MEG channel. So this is what is output. Well, this is what is learned in the fitting stage as each of these coefficients. Then step 2 is to get the actual predictions of the model. So here I give it we just need the brain data of the test trials to get the predictions. And here I'm getting out probabilistic predictions, which isn't something that I went into, but this is an output of the logistic regression. You can get not just was the label 0 or 1, but basically how far was the trial from the decision boundary, i.e. how confident is the classifier about the label that it's going to assign. So if it's very close to the decision boundary, the certainty is not very high, so it'll be close to 0.5, whereas if it's very certain in either direction, it's going to be further from 0.5, either closer to 1 or closer to 0. And here I'm plotting what the truth was. So the truth is either 0 or 1, and then we have the corresponding prediction of the classifier. So the predictions tend to be closer to 0 when the truth was indeed 0, and the predictions tend to be closer to 1 when the truth indeed was 1. And then the final step is to actually, rather than we don't look at the final step is to get an output of the actual performance accuracy. So in this case, so I said I'm using the area under the curve just to compare the true labels of Y to the predicted probabilistic labels of Y. And in this case, we do pretty well. So this is actually 99% accuracy for this data set, for this subject at this time point. Okay, so I think that I've probably talked enough. Just briefly, there's a lot more in this notebook here, which I'm hoping is going to be useful to people. So I go through how you basically apply this to different features, how to get the temporal resolution of the accuracies over time. You can see that there's different lines here that corresponds to different folds of the data, so different splits of the cross-validation scheme. And I show this for both categorical variables as well as for continuous variables as well, and then how you might combine both categorical and continuous into kind of a single visualization.
Okay, thanks. That was really cool. So we have a couple of questions. So the first one is what percentage of the data should be used as the testing set for iteration? I actually want to add to that because I know you mentioned the 80-20% split, but I'm wondering if you vary that split based on the conditions of the experiment or the data you're analyzing and how you make that decision.
Yeah, so I'll typically train on 80% and then test on 20. This is, I guess this is always something that you can split your data into 3 parts and then actually try different splits of train and test and see what does better for your data. But this has been a pretty good choice for me so far. I think being able to training on more data than you're testing, it allows you to basically stabilize the weight. So it's going to be a trade-off between how much data you allow yourself to train on means that the actual estimation of the coefficients is going to be more stable. And you also want there to be sufficient variability from split to split as well, which is part of why I think that leave one out cross-validation has kind of gone out of popularity. Because so in leave one out cross-validation, you're training on everything other than one trial. And then you loop through, so you leave out a single trial each time. But the problem there is that what you're training on is super, super similar from split to split. So if there are any kind of biases in your data, all of your splits are going to be victim to those biases. So allowing there to be more variability across what you're training and testing means that if there are some biases, then it's not going to be there in all of your splits. So you'll have a more representative idea of how good the decoding performance is overall when you average over them.
Okay. I'm just curious to like a question relating to that. So would you showed the example of random sampling of the different trials. Would that have the same issue? Did that make sense?
So I think that with random sampling, you avoid more issues than, so like if there are biases, then maybe that's going to be, you can imagine that there are certain biases, but only within a subset of the data, and that there might be like temporally contiguous. So if you randomly sample like throughout the duration of the experiment, then you're again just essentially allowing this variability to be random. And so once you kind of average over the different folds, then that randomness will average out, as opposed to, yeah, if you have the more structure you have in the cross-validation scheme, then the more susceptible you'll be to kind of introducing non-random noise.
Okay. We have time for one more question, I think. So Maya asks, says, thanks for the great talk, Laura. Do you perform nested cross-validation? Otherwise, aren't we double dipping the data by using the same trials for train and test in different partitions?
Yeah, so I don't, yeah, the split is always separate. So you're never training and testing on the same trials. And typically I don't allow there to be overlap between one fold and the next. So what I choose to test on in one fold will never enter the test set again in the other folds.
Okay, cool. Yeah, thanks again for the great talk. There's a few more questions in the Q&A if you want to take a look at those and respond to them. We'll move on to Aaron Nidiffer. So Aaron Nidiffer completed his PhD at Vanderbilt University and is currently a postdoctoral research associate with Edmund Lawler at the University of Rochester. His research uses both complex artificial and natural stimuli to explore the neural underpinnings of audiovisual binding and the unique contributions of visual signals to neural tracking.
So you see my screen?
Yes.
Great. Hi, everyone. I'd just like to start off today by thanking the organizers, Nate, Mick, and Gio, for inviting me to chat today about these topics related to some of our recent work with the MTRF toolbox. And also, I'd like to thank them for subsequently inviting me to be an organizer for the workshop. It's been a good time chatting with the lads over the past couple of months, and it's nice to see this come to fruition. I'd also like to, as I put on the organizer hat, I'd like to thank the speakers who have already given talks, and look forward to the speakers who will be giving talks in the future. So earlier we've heard about some of the modeling process itself, and now I'm going to tell you a bit about some of the important considerations when modeling multivariate stimulus features to extract their neural responses, and give you a little bit about how some of them, the MTRF toolbox can handle those. Currently and in the near future, we have some planned additions to the MTRF toolbox. And so just to say at this point, speech and language are obviously a strong focus in linear modeling and in this workshop itself. So I'll give examples mostly involving speech of some kind, but we can use these techniques to model brain responses to generally any kind of multivariate features, or specifically stimulus that has features that span different types. So a lot of meaning and information can be crammed into simple vibrations of air, and then those vibrations are transmitted to a listener. If someone is around to hear what we're saying, their sensory and perceptual systems have to take those vibrations and those sounds and then analyze them and process them and then reconstruct them into that information that the speaker was actually trying to convey. And so like understanding this process has been a big focus on linear modeling of speech. And we've started by understanding language, how it's subdivided in based on a hierarchy that spans from speech sounds, which to my mind carry very little innate meaning in and of themselves. They can, but they don't necessarily, to meaning that changes depending on the context. And so like this process of understanding how we go from speech sounds, which are categorized into phonemes and tracked phonemes over time to form words, which are grouped into phrases and sentences, which give rise to meaning. That's one of the big goals of linear modeling of speech. Meanwhile, brain structures, as Ed pointed out earlier, that are involved in language processing have been described in a hierarchical manner that somewhat reflect the linguistic hierarchy that I showed earlier. The process starts with a spectrotemporal analysis of the incoming sounds. It begins at the periphery, actually, and extends all the way up in the cortex. And this analysis gives rise to phonological and lexical and conceptual networks that build upon the previous networks and reciprocally affect those lower networks. And so when you want to make sure someone knows that you don't like sand, and really don't like sand, the brain processes the incoming sounds at multiple stations and stages to fully understand that hate. So one of the biggest hurdles in linear modeling of speech is how we characterize the relevant features of our stimulus to reveal the appropriate brain activity at the appropriate steps. For example, Anakin's statement can be described by its waveform, the physical stimulus of the sound, and that physical stimulus can be further processed into its intensity along different frequency bands, and we call this the spectrogram. This is important. We know that frequency is important in speech. For example, these high frequencies tend to represent sibilants and are important for those. Formants or harmonies of speech or harmonics of speech are important to differentiate phonemes. Those formants and also the fundamental frequencies, the lowest frequency here, can affect timbre and help to indicate speaker identity. And changes in the fundamental frequency can indicate context, or, for example, are we asking a question or stating something? From this representation, the spectrogram, we can combine across the frequency into a feature that is well used in this line of research, the stimulus envelope. And so these two reflect the acoustic signal themselves, but we don't have to rely on these measures that are derived directly from the acoustic measure. For example, we can use the output here, a model of inferior colliculus neurons that have been fed the acoustic signal. And so our lab has been working on that recently. Further, we can look at higher order features. So from this spoken sentence, we can derive a list of phonemes, and we can group those phonemes into their constituent phonemes or phonetic feature and represent them over time and have a discrete like yes or no model. And we can ask phonological questions using this feature. And then further from the words, we can enter those into a model of word meaning. Here I'm showing from Michael Broderick's 2018 current biology paper, where he used word2vec to characterize a word's representation in speech. And we base a measure on the correlation of a current word with previous words in the context. And so we can use all of these features to analyze speech and to try to extract the neural representation at different stages in the processing hierarchy. But we can't just jam each of these features through a TRF, as we say. There's several impediments to this. First of all, and probably most importantly, and one that I will cover the most today, is that these features, because they're coming from the same stimulus, they tend to be correlated over time. And so they're going to share some explainable variance, and that's going to need to be taken care of. Another thing that I'll cover at the end is how to optimize your regularization in order to accommodate different feature types. I won't cover this one as much because it's in my mind not as important, because if we mess up the correlation part, then we're going to be biasing our predictions to give us false positive. If we miss this, then we are going to just have a suboptimal fit. But another thing that bears mention is that different features could be affecting the responses of the brain at different time lags, and so we have to be aware of that. So to go into the correlation of the features, I'm going to give a bit of a tangible example, a bit more tangible example that it seems kind of silly toward the end, but I think it'll help to really give you something to grasp a hold of. Here I'm showing 3 decoder models that were collected during an experiment during 3 conditions. One condition where participants were listening to auditory only speech, one where they were seeing the visual speech but not hearing the sound, and one where they could see and hear the speaker talking at the same time. All 3 of these were fit using the stimulus or the acoustic envelope. So in the auditory, we see strong coefficients over typical auditory areas in the EEG response. Just a quick note here, there was a question about these topo plots. There are 2 flavors of topo plots. The one I'm showing here shows the coefficients of the TRF, and they represent sort of how strong the TRF is represented at some particular time and over some particular space. I'll show another one later that relates to the prediction accuracy, but we'll stop with that for now. In the visual condition, you see 2 hotspots over visual cortex, which might seem kind of weird given that we're regressing to the acoustic envelope, and in the audiovisual condition, you see both. But in the visual condition here from another experiment using, I think, the same data or the same speech stimuli, we see that the envelope does produce a nice, pretty TRF with a nice peak at a time that you would expect. And that peak is centered around the back of the brain. So what exactly is happening here? Is the visual system seeing or hearing the acoustic envelope? I think you probably know the answer to that question, but to get into it a little bit more, we need to consider what's going on in the visual stimulus. As the mouth opens and closes, so does it affect the acoustic envelope necessarily, because the mouth is actually shaping the acoustic envelope. So when we look at those 2 features side by side, we see that they're nicely correlated with each other. And this is pretty typical of audiovisual speech. And so what's actually happening is that the envelope is correlated to something that's happening in the visual system, or the visual signal itself. Here, Aisling has used motion to characterize a TRF instead of the envelope and found basically the same result. And further, later, we actually made a model explicitly detailing the lip movements themselves, and we've shown that it is a better model to predict things going on over the visual cortex. This is the second type of topography that I was talking about. This represents the prediction accuracy. Here, these can be both positive and negative, and where positive means there's a positive inflection in the EEG activity, or in this case, in the stimulus, because these are decoder models. What this represents is how strongly represented that signal is in certain electrodes, or how well that stimulus can predict EEG activity in certain electrodes. So because we can better predict EEG activity with lip movements, we know that no, the visual system is not seeing the acoustic envelope. Fortunately, Mick and Aisling did not make this mistake, because they used their envelope predictors in such a way that didn't rely on this interpretation, or they didn't make this interpretation, but you know, it can happen to you. So just be careful. It's important to consider, for that reason, what features of the stimulus are important to us, and which features need to be accounted for in the analysis. This can be quite a cumbersome process if we have a lot of different features, but today we'll keep it simple. Say if we want to make a phonological claim, it would be important to rule out responses related to phonemes and phonetic features can't simply be attributed to the spectrotemporal features of the speech sounds. Like Ed said earlier, if we were a robot and we said ah the same way every time, these two would be strongly correlated. Because we don't say ah the same way every time, there's a bit of a dissociation there, but they still do share some variance. So it's important to account for that. So how do we account for the variance shared between these stimulus features? The first way I'd like to show you involves forward model selection. And the logic is as follows. So if we fit two models, a spectrogram model and a phonetic feature model, trying to predict EEG, we see that some of their ability to predict is shared between the two features. This might be related to the timing of the phonemes and the timing of the onsets and what have you in the spectrogram. It's not exactly sure, but they do share some variance, and presumably they may or may not have some unique contributions to their ability to predict EEG. So one way of handling this shared variance and extracting, or kind of trying to quantify this amount of unique variance, or at least the presence of unique variance, is to combine these models into a joint encoding model, and then compare it to the constituent single feature model. So what this looks like is comparing spectrogram and phonetic feature model to the spectrogram model, and the amount that it wins by is presumably related to phonetic features. So several different speech representations were used here to model EEG signal that was recorded during an audiobook. Both acoustic and phonetic features were contributed predictive power to this, and we find this by fitting single spectrogram and phonetic feature model, as I showed before, and then a joint model, and then we can compare this joint model to the individual models, and lo and behold, it does outperform. And so we can say that there is some unique contribution from both of these features. Typically, when we fit these models, we take a set of trials, as Laura talked about earlier, and we associate them with a neural response. We take some subset and fit them, and then predict on some remaining trials, and we can quantify the effect of whatever stimulus feature we have. We can also measure the noise floor, and Nate will talk more about this later, by shuffling the trials. I just want to take another aside here and mention maybe the difference between shuffling stimulus features and before and after fitting the TRF. If we shuffle the features before the TRF, we are really testing the modeling procedure. So how well can a TRF pick up on effects that are related in between trials, and that don't really necessarily map on between the stimulus and the brain response, but are sort of inherent in the stimulus feature themselves. If we shuffle afterwards, we're testing the model's ability to predict incorrect data. So I tend to favor shuffling the stimulus feature before fitting a TRF and then seeing how well that TRF can predict what it's supposed to predict. But anyway, so when we shuffle the TRF features, we get a TRF shown in the dashed line that's not as robust as an intact TRF. When we try to predict its neural response, we see that it falters. And this gives us an estimation of the noise floor for this particular feature or for the model. We can apply the same logic when we have multiple features to remove the effect of one feature by shuffling only that one feature. And so presumably we should get an intact feature, TRF for one feature, and reduce the effect of the TRF for the other feature. And we can do this for both features. And when we do that, we can see that when we're going from a spectrogram only model to a spectrogram model that has the shuffled phonetic features, we do get a small boost of performance, but it's nothing compared to what happens when we have an intact phonetic feature model combined with an intact spectrogram model. So this is really useful when we need to talk about the presence of multiple features in EEG signal or whatever neural signal you're talking about. But what happens if you need to isolate the individual features a bit better so that you can say, for example, compare their effects across conditions? One way to do that is by fitting a joint model and then separating the feature weights afterward, before prediction. So here we're seeing same thing as before. We have an acoustic model and a phonetic feature model that were fit separately and predict EEG separately. And just as before, we have a joint acoustic phonetic model that is fit together and produces a joint fitted MTRF. Importantly, the MTRF that's related to the phonetic features will differ somehow from the individually fitted MTRF, and so will the spectrogram feature, and will do so in a way that sort of accounts for some of their shared variances. And so then we can split those models into two different individual models and then see how well those individual models can predict EEG activity or whatever neural response. We can compare the joint fitted model with the single fitted model. We don't have data on this on the MTRF because the functionality for this isn't, sorry about that. The functionality for this isn't complete, but here's an fMRI experiment where individuals were watching videos and they characterized the videos in terms of like the object category and some motion that occurred in the video. And what they're showing here are the activity over voxels that are different between a joint fitted model and a single fitted model. So when you subtract the single fitted model from a joint fitted model, what we find is that in the single fitted model, there's activity that spans the swath of visual cortex from the lower areas to the higher areas, and you can see that here in green. But when they fit the model with both features together and then looked at just the object categories, the lower visual region correlations went away. So they are essentially labeled here as spurious correlations that were dealt with by fitting a joint TRF. And the converse happens when looking at motion energy. Motion energy is restricted to lower visual cortex, and joint fitting removes some spurious correlation in higher visual areas. If we want to take a bit more of a whack at the features that are irrelevant to us, we can actually partial them out. And this starts off in much the same way as fitting any TRF feature. We've got a set of trials and with some features and their corresponding EEG data. We can fit the TRF and then test on some left out trials. We can predict the EEG for those left out trials. And then for each of the trials, we can just simply subtract them from the EEG activity. And what we're left over with is a residual EEG signal that presumably contains none of the effects of the original feature. As a sanity check, we can then go back and try to refit the original feature. And when we do that, we can find that there's no ability to predict whatsoever. To give a bit of a conceptual backbone to this, if we consider this gray box and then anything inside the black box is the total variance of the EEG. Anything in the purple is explainable variance, and it doesn't always look like, it probably never looks like this. This is an idealized model of EEG. It's going to be much more messy than this. If we're able to explain this EEG or explain the explainable variance by only two features, a red feature and a blue feature, when we fit to the red feature, we're going to be fitting a little bit to the blue variance, and vice versa. Blue variance will fit a little bit to the red feature. So when we fit to feature 1 here, we can remove that feature, and then trying to predict it, we actually get nothing because nothing is left. And so remaining here is the rest of the blue feature, which we can then predict using its feature representation and see the effects of that feature independent of the original feature. So we did this with some participants who were watching videos of silent speech. We wanted to show some effects of visual phonemic processing, or VISEMs, in the data. So we fit model to lip movements and to the VISEMs, and we see that they each contribute some bit of variance, but we wanted to isolate their variance to show that one or the other is going to be affected by some manipulation. So when we partial out the same feature, we see that VISEMs can't predict VISEMs when they're not there. Lip movements can't predict lip movements when they're not there. And then we can fit those features after partialing the other feature. And so this is the partial feature that you saw previously, and this would be the VISEM feature after lip movements are partialed. We did this not just to get an idea of the VISEMs by themselves or the lip movements by themselves, but because we had some conditions where participants were able to rehearse some videos before the EEG session. And so we wondered where in the system any enhancements might be bestowed by that rehearsal. So we were looking at occipital channels and comparing the novel videos that they had not seen before to the videos that they had previously rehearsed. And it looks like there is some marginal improvement to lip movement. It turns out it's actually not significant, but we wanted to make sure of that because, of course, VISEMs could be contributing to this model and lip movements can be contributing to this model. So we removed the effects of each other model, and we showed that after rehearsal, it was strengthening the effects of the VISEMs, but not the lip movements. So finally, I want to talk about how we can optimize the fitting procedure when the stimulus features are drastically different. And so this really matters when you're having these features that are continuous, like a spectrogram or an envelope, or are discrete, like stick models that are like phonemes or VISEMs or word onsets and so on. And the way we can do that is by banded ridge regression. So here we have the closed form solution to ridge regression to derive our TRF model, the beta coefficients, from the X and the Y. So X here is our design matrix of our stimulus vector, and it can include multiple features and multiple time lags. Y is our EEG signal, and here XTX represents the covariance of our stimulus features, and this is what it looks like. So when we covary, or when we look at the covariance and the autocovariance of the spectrogram, it looks like this, and when we look at the same thing for the phonetic features, it looks like this. And so these covariance autocovariance matrices for these two features look drastically different. In ridge regression, our ridge parameter tends to be a single value that emphasizes the main diagonal. And so this can be problematic. It can be suboptimal when we're trying to fit these multiple models. And so ridge regression sort of alleviates this problem by regularizing the features separately. And so this is a new function in the MTRF toolbox that we are planning to release relatively soon, but we don't have data from it. So we're looking at the same MRI data from the previous couple of slides back. Here they are trying to predict EEG activity to semantic object features and to the motion. And when they use a banded ridge parameter as opposed to a ridge parameter, we see that most of the time it does a better job at predicting the fMRI signal and in our case, the EEG or MEG signal. And with that, I will give a short summary here. So here are some of the tools that I've discussed. There are other tools, but these are the ones that I feel are most important and probably the easiest to understand. Forward model selection, shuffling individual features, the separating features after joint fitting. This one will be possible in future versions of the MTRF. It requires banded ridge, which is not completely finished. Partial correlation is another functionality that is pretty much finished at this point, but will be part of the MTRF toolbox in a future release. And of course, banded ridge regression. And with that, I'm happy to take any questions.
Thanks, Aaron. That was great. So there's one question here, a more general question on stimulus features. So Talat asks, what envelope extraction method is more reliable for broadband envelope? Splitting the speech signal in narrow bands according to frequencies, using Hilbert transform for each band, and then summing up those for the broadband envelope, or using MTRF toolbox function MTRF envelope to calculate the moving RMS envelope?
Mick might be able to answer the question better about the envelope, but in my experience, they don't typically produce like very wildly different results, and we don't get much of a benefit whenever we like add any sort of like fancy analysis or processing steps to the envelope extraction. I'm familiar with a lot of papers that have split into different frequency bands, characterized the envelope in each, and then summed across. I think that might help out with like not canceling out of different frequency bands or something, but typically it doesn't give us much of a boost or anything like that. And especially if you're doing something like envelope tracking. So as Ed mentioned earlier, the envelope is not like a monolithic thing. So things going on in the auditory system are, there's a lot of stuff happening, and to characterize it with an envelope is quite a one-dimensional, well, it literally is one-dimensional way, which is fine for certain things, like just saying that the EEG is tracking the stimulus. But if you're trying to get more and more out of your TRF and the fitting procedure, adding sophistication to an envelope extraction isn't really going to buy you much of anything.
Okay. It looks like Giovanni wants to speak.
Go for it.
Yeah, I mean, that was a great point. I just wanted to connect what you said to a question that we got at the very start, which was about, why don't we do this with nonlinear models, for example, which I found your slides were quite clear about one of the points that we are trying to make with these kind of methods, when you study this overlap between two different features, for example. But the reality is that, also about this question on the envelope, what's the best way to get the envelope? So the question one should keep in mind is, what are we trying to model? So for example, if now you take a spectrogram, right? Let's take a whole spectrum with lots of frequency bands, and maybe you could even have a speech model. I don't know, a model that you derive from speech recognition tools. And so then maybe you can try to fit a nonlinear model between the spectrum and the EEG, right? But in that case, this nonlinear model is capable of representing the phonemes as well. So you're introducing a nonlinear model that can take the spectrum and represents and transform the spectrum into lots of stuff, including phonemes. And so there, you can't discern things as well anymore as you can do with a linear model. The linear model can help to do this kind of separating different features. So about the envelope, yeah, just what do you want to model and why do you want to do that? So that's the main question to keep in mind.
Thanks, Joe.
So there aren't any more questions.
There's more to come later.
Yeah. So I guess we can call it there. So in another 15 minutes, we'll start the hands-on tutorial. So we'll do a break for now. So we'll see you later. Joe, did you want to say anything? Okay, he gave me a thumbs up. So all right, we'll see you later.